Thanks for watching this video. I am going to introduce our paper, Class-Wise Metric Scaling for Improved Few-Shot Classification. Few-shot classification aims to generalize basic knowledge learned from a large-scale available dataset in the meta-training stage, and recognize novel categories with only a few labeled samples in the meta-testing stage. In previous studies, nearest centroid-based methods have attracted considerable attention due to their simplicity and effectiveness. The main idea of centroid-based methods is to pre-train a general feature representation that can separate target unseen class clusters. For addressing a target few-shot task, a nearest centroid classifier is built with the feature embeddings of the few annotated samples. Generally, each class centroid can be calculated by the mean of the embeddings of the class. It is worth noting that the nearest centroid method only uses a single feature vector to represent a class. Such limited class representations become an advantage in the few-shot learning, as it effectively alleviates overfitting. However, we consider that those methods intrinsically ignore per-class distribution. Concretely, we describe our motivation by a binary category classification scenario. Under the centroid-based metric with the nearest neighbor rule, the decision boundary lies in the middle of two class centroids. However, the class 1 is more widely distributed and has a larger intravariance than class 2. Intuitively, a more reasonable decision boundary should lean to class 2. In order to refine the biased classification decision, we propose a simple yet effective mechanism, class-wise metric scaling, which multiplies the vanilla class-agnostic distances with class-wise metric scalars. So the diversity of intra-class variances can be implicitly considered to improve the target classification accuracy. We apply class-wise metric scaling to both meta-training and meta-testing stages. In the meta-training stage, we adopt a conventional supervised training procedure, which pre-trains a feature extractor combined with a distance metric-based classification layer. Particularly, metric scalars are simply set as learnable parameters that improve feature representation transferability. In the meta-testing stage, the class-wise metric scaling is performed by an optimization problem, where metric scalars are obtained by optimizing likelihood on the support set directly, which facilitates task adaptation. Fortunately, the optimization problem is convex and low-dimensional. Here is the overview of our CMS model. Based on the pre-trained feature extractor, the support image features are used for producing the optimal metric scalars. Finally, for a given query sample, the prediction is assigned by metric scale distances. Experimental results show that our method CMS has achieved state-of-the-art results on mini-ImageNet, tiered ImageNet, and cross-domain benchmark datasets. For example, CMS achieves the mean accuracies of 66.64% and 83.63% for 5-way 1-shot and 5-way 5-shot settings on mini-ImageNet dataset, respectively. We can interpret CMS as the Gaussian mixture model. For a given n-way classification task, we can assume the feature point set follows a Gaussian mixture distribution. For simplicity, we consider spherical Gaussian distributions with a particular uniform variance. And conditional probability can be derived to the form which equals to CMS, in which case a class scalar is conditionally equivalent to the reciprocal of the class variance. So CMS essentially allows for more flexible class representations, which implicitly captures the intra-class variances. Further, we also extend CMS to two kinds of semi-supervised few-shot learning, that is semi-supervised transductive and semi-supervised inductive modes. We simply leverage pseudo-labeling and cherry-picking skills to address both semi-supervised few-shot learning uniformly. Our goal is to augment the support set by picking the samples with high confidence. So meta-testing procedures also remain the same as in the standard few-shot learning setting. We experiment on the mini-ImageNet and observe significant performance boosts which are significantly improved compared to the standard few-shot learning and achieve state-of-the-art results as well. In summary, we propose a class-wise metric scaling approach that improves the nearest centroid-based method. In the meta-training stage, CMS improves representation transferability. In the meta-testing stage, CMS facilitates task adaptation by a convex optimization. Moreover, CMS can be mathematically interpreted as Gaussian mixture model. In addition, we also extend our CMS to semi-supervised few-shot learning. Finally, we achieve SOTA performance on multiple benchmark datasets. Thanks for your attention.